So in today's discussion, so we have spent the 5 sections of chapter 5 to go from the beginning of what is motivating you guys for integrals, what are integrals, and we said, okay, we are trying to find the area under the curve. We started with a positive continuous function, and we said, okay, we want to calculate the area under this curve. You remember that's where the journey started, right? We started from the time that we said, okay, we want to calculate this area. Then you remember we started with a strip, creating strips, we call it a regular partition, and flattening the tops of them and calculating the area under each of those, and then adding those together, then taking the limit as I have more and more partitions. So as n goes to infinity, the number of partitions goes to infinity. That was what we did. Then later we said, okay, so we can actually do this a little bit better using fundamental theorem calculus, or more accurately, if I just, and simpler, if I just find the antiderivative. So we build the connection between the integral, the definite integral AB, and antiderivative of f. So that was the fundamental theorem calculus that built the connection between those. And so we can evaluate an antiderivative, a definite integral this way. Talking about, again, calculating the areas, but then it could be net change, because your function could be a little bit above, it could be a little bit below. So it would be the net difference between positive and negative areas. So that's what we talked about later. And then, of course, when we got to 5.5, we talked about, since we're trying to calculate the antiderivatives, we talked about the methods of calculating antiderivatives. If it wasn't just a clear function that we could find antiderivatives right away, hopefully we could use something like substitution in solving it. But of course, chapter 7 is filled with different techniques of integration. So when we get there, we are going to look at that as well. But for now, we're dealing with just a simple substitution as a method of integration, or a technique for integration. Today's discussion in section 6.1 of your book, we're kind of going back to the idea of the areas, but now we're going to make it a little bit more fancy, because now we can actually calculate the areas between curves, and we can do it better than taking the limit, because we're going to be using antiderivatives and fundamental theorem calculus. So the idea for that is, if I'm given two functions, say f of x on the top and say g of x on the bottom, and if I want to calculate the area that's bounded by those two, simply we can calculate the area that's below f and calculate the area that's below g, and the difference would be the area that I'm interested in. So the area, which would be the blue shaded region minus the red shaded region, is really just integral of f of x from a to b dx minus integral from a to b of g of x dx. Or if you put it together, you get integral from a to b of f minus g dx. So that's the idea. If somebody gives you two functions and says find the area between those two functions, you always subtract top minus bottom. Now, it doesn't even matter if the top and bottom are below or above x-axis. So for example, if your function is, this is your g and this is your f, and you want to calculate the area in between them, you still subtract the top function minus the bottom function. Even though if you calculate the distance from the x-axis, f is farther away, but you still, because they're in the negatives, you subtract the top minus bottom. It's kind of like saying, if I want to find the distance between -1 and -3, I don't do -3 minus -1. I do -1 minus -3. Always the top minus bottom, always the value to the right minus the value to the left. Okay, so that's how you would calculate the area bounded by two curves. That's really basically the idea of this section. Calculate the area between two curves. Now, let me just do a quick example just to show you guys. If, for example, the two curves that are given is, say, this is number 13 from your homework. If y is 12 minus x squared and y is x squared minus 6. Now, it doesn't hurt to quickly sketch it just to see what the graphs look like. So 12 minus x squared is a parabola that looks like this. And x squared minus 6 looks like this. And then there's a point of intersection between the two curves that you can find. And you're trying to calculate the area bounded by these two. First, you have to figure out which one is on top, which one is on the bottom. So this is going to be the top graph. This is going to be the bottom graph. This is y equal to 12 minus x squared. This is y equal to x squared minus 6. So the setup of the integral would be integral top minus bottom. But you need the bounds. To find the bounds, you set the two functions equal to each other. So you go from -3 to 3. And that would be the area that you're trying to find. Okay. Now you could, let's just finish this one for an example. Now let's practice one of the things we learned last class when we were dealing with the even function. Obviously, this is even because if I change x to a negative x, I get the same function back. So I can write it as a double of the area from 0 to 3, which visually also, I think you guys agree, that if I just calculate the area from 0 to 3 and double it, I get the full area. But here I'm just looking at it algebraically. This gives me a 0 as one of the bounds, which makes calculations a little bit easier. Antiderivative of 18 is 18x. Antiderivative of 2x squared is 2/3 x cubed. Again, add 1 to the power and divide by that. 18 times 3 minus 2/3 times 3 cubed minus 18 times 0 plus 2/3 times 0 cubed. You'll get faster at this. So this part cancels out. So you just get 54 minus 18. $72. Again, this is area between curves, so the answer should be positive, right? Top minus bottom. You're trying to calculate the area between the two curves. Now, if I change the same problem, if I just slightly modify it, instead of saying from just the area bounded by these two curves, and say, how about the area between -1 and 2 between these two curves? So what if I say, like, again, we have the same two parabolas. And if I now want to go from, say, let me write down the equations one more time. If I want to say now go from -1 to, say, 2, and find this area, you still are going to do the top minus bottom. But your bounds are -1 to 2 now. You get a smaller. That's how the calculation works. Okay. Now, same function again, same two functions. If now I say, oh, let's do this. Let's do it by integral from area bounded between the two graphs, not from -1 to 2 that it was here, or -3 to 3 that was here. What if I said do it from 0 to 4? Now, why 4? What makes 4 special? Because 4 4 is actually passes 3, which means the functions change relationship. From 0 to 3, 12 minus x squared is above x squared minus 6. So you do that subtraction, top minus bottom. But from 3 to 4, if somebody says find the area bounded by two graphs between 0 and 4, from 3 to 4, now the top function is not 12 minus x squared. Now the top function is x squared minus 6. That falls above. So it's going to be x squared minus 6 minus 12 minus x squared. Both pieces have to be positive. So you get an integral from 0 to 3 of 18 minus 2x squared. And then you get an integral from 3 to 4 of x squared minus 18. Switches. Okay. 2x minus. And whatever that number turns out to be. Calculate that. So if they give you limits, if they give you bounds, you have to pay attention in between those two bounds. Do the functions switch roles? What was above becomes below, comes below the graph. What was below becomes the above graph. If they don't, then don't worry about it. Just integrate from left to right, top minus bottom. If they do, you have to consider those changing points, wherever the two change relationships, and make sure you always subtract the top minus the bottom for every case in that. One of the examples I like is the area between the graphs of y equal to sine x and y equal to cosine x, those two graphs, over the interval 0 to pi over 2. One of simple but still nice graphs. So sine x, of course, you all know your sine x's. So this is pi over 2. Sine x goes to 1 at pi over 2, and then it continues, but I don't care about the rest of it. Cosine x starts from 1 and it goes to 0 at pi over 2. So that's sine, that's cosine, again, to the best of my drawing. There is a cutoff. There's a point where the two switch. First, cosine is above sine here, and then sine is above cosine here. The two are supposed to be the same size. My drawing is slightly off. So from 0 to that number, which I have to find out, is cosine on the top, sine at the bottom. From that number, which I have to find out, to pi over 2, sine is on the top, cosine at the bottom. That number comes from solving sine x equal to cosine x. And again, if you are good with your trig, you probably remember that one way of doing it is by dividing by cosine, both sides. So you get tangent of x equal to 1, x would have to be pi over 4. So it goes from 0 to pi over 4 and from pi over 4 to pi over 2. The two are the same, so you could double, but or you can just calculate them. So the derivative of cosine is sine. And the derivative of sine is negative cosine, so your negative becomes positive. And then this one, you get negative cosine minus sine. And the sine of pi over 4 is root 2 over 2 plus root 2 over 2 minus sine of 0 is 0, cosine of 0 is 1. Cosine of pi over 2 is 0, sine of pi over 2 is 1. And then maybe group them together nicer. Minus cosine of pi over 4 is root 2 over 2. Sine of pi over 4 is root 2 over 2. So I get root 2 minus 1, negative 1 plus root 2. So I get 2 root 2 minus 1 minus 2. And of course, root 2 about this is 1.44. So I get 2 root 2 minus 1, which is about 0.44, about 0.88 if I did the calculation correctly. Okay. You can use even odd function here just because you are dealing with not symmetric interval. It's not around 0. It's just from 0 to pi over 2. You don't have the symmetry there. Now, one of the problems which causes some issues for students is this one, the area between x squared and x cubed. Now, it seems like easy enough, right? Just draw the graphs and figure out what happens there. And in fact, you're right. It's pretty straightforward. You draw the graph of y equal to x squared. And draw the graph of y equal to x cubed. As you can see, it's not very smooth drawing. And this is the region you're talking about. Now, the point of intersection, if I said x squared equal to x cubed, or x squared x minus 1 equal to 0, x would be 1 or x would be 0. So those would be the, what I did was I took x squared to the other side and then I factored out an x squared. But you could do it quicker if you wanted to. So of course, 0 and 1 is clearly what the picture shows as well. So I know my integral is from 0 to 1. And students always wonder, so how do I know which graph is up, which graph is below? And of course, you can use your calculator. You can just show which calculator, which one falls on top, which one's on bottom. But if you want to do it by hand without actually drawing the graphs precisely using your calculator, or better graphs using your calculator, you can just pick a number in between the two, say 1/2. And then ask yourself, is 1/2 square bigger or 1/2 cube bigger? Of course, 1/2 square is 1/4. 1/2 cube is 1/8. Obviously, 1/4 is bigger than 1/8, which means the square is actually above the cube. Even though conventionally you think that cube is bigger than square, but for numbers between 0 and 1, when you square them, you actually, the higher power you take, the smaller the number gets. So it's actually x squared minus x cubed. For something like this, though, I mean, I don't want you to have that practice, but you could just calculate the number and you will get a negative number if you do the other way around. But it's not a good practice just because there are some flaws to that logic, for especially when the graphs switch direction, switch relationship. So 1/3 x cubed minus 1/4 x to the 4 from 0 to 1. So you get 1/3 minus 1/4 minus 0 minus 0. So you just get 1/3 4/12 minus 3/12. If I get a common denominator, which is 1/12. So that's how you would you would calculate the difference, the area in between. Okay. Now there is something else to consider, and I can highlight that looking at an example. It's actually, this is an example from the book, but the function would have been the same thing I would give if I were to do this lecture myself, because it's just a very nice combination of functions that make this look very clear. And this is actually, as I said, example 7 of your book, but it's not anything special about the example. It's just that those two combination of functions makes very nice demonstration of what we're trying to say here. If I have y equal to x minus 1 as one of my functions and y squared equal to 2x plus 6, the graph of these two would actually look something like this. And again, I believe your book draws it much better in this case. but this is my best attempt at it. Looks something like this. When you're trying to calculate it, and of course this is -2, this here is 4, and I'll tell you guys why that's important. 5/4 is going to be this point because this is 5, and this point is going to be -1, -2. Again, why is that important? I'll tell you in a second. If I were to do this the way that I have introduced to you guys so far, I would have to split the region into 2 pieces because clearly I don't have the line always below the curve. There is a line below the curve here, obviously, but in this region, there is no line below the curve. It's really just the area between the curve and itself, one plus of the curve and the minus of the curve. So I couldn't just integrate in a single integral, find the area from one point to another point. I will have to split it into 2 pieces. And it's not that's not doable. You can do that. You can recognize that this graph is, if I solve for y is plus or minus square root of 2x plus 6. So if you really want to do it in pieces, you could do integral from, of course, this point is -3. So I could do from -3 in the x direction to -1, that's one, of function, top function, which is going to be positive square root of 2x plus 6, minus the bottom function, which is negative square root of 2x plus 6 dx. And then from -1 to 5, the top is positive square root of 2x plus 6, and the bottom is the line, which in this case is x minus 1. So it is doable. You can do, this would be the blue portion, this would be the red portion. And you can calculate it. You can calculate the blue part and then minus the red part. I mean, plus the red. Totally acceptable. It's just, imagine having to calculate those integrals also. So a couple of drawbacks here. You have 2 integrals to calculate, and the integrals are not very friendly. And along with all the work you have to do to visualize what's going on and so forth. But what we offer you here now is, then why are you so attached to using x as your independent variable? Why are you so attached in creating rectangles that look like this from one graph to another graph? Why can't we instead look at rectangles that look like this, where our delta is not delta x, but delta y in the y direction? The advantage of that, as you know this, is you have a clear function on top. If I look at it from right being positive, left being negative, this function is on the top, where this function is clearly on the bottom, is to the left. So if I do right minus left, as I did top minus bottom, I think I can calculate this. The only drawback here is, again, I have to use y as my independent variable rather than x, which is not really too bad. So the equation of the line was y equal to x minus 1. Instead, I'm going to say x is equal to y plus 1. So I'm going to convert it as a function of y rather than a function of x. And the other function, which used to be, it was a function of y, but it was expressed in terms of x. I would say x is equal to y squared minus 6 divided by 2, solving for x in both cases. Doing it that way makes me simply write in terms of y, as y goes from -2 to 4. So it goes from -2, the bottom bound, to 4, the top bound. And you subtract right minus left instead of top minus bottom. Right is y plus 1. Left is y squared minus 6 over 2. So yes, indeed, you can calculate the area between 2 curves, not going in the x direction, but going in the y direction. Not having delta x, but having delta y. Not calculating top minus bottom, but calculating right minus left. In calculation, of course, let's just finish this problem since it seems very pleasant. Antiderivative would be -1/6 y cubed plus 1/2 y squared plus 4y, just power rule all the way around. Plug in the 4. Plugging in the 4 for the top part and the -2s for the bottom part. I added 8 and 8, I got 16 as subtracting. 7 to 16, the sixth. So that would be the area between the two curves. Again, you expect a positive number because it's the area between the two curves. So that's basically what this homework was. There's a lot of problems that says, okay, sketch the region that you're calculating the area of, what's on top, what's on the bottom. Draw a sample rectangle, and by a sample rectangle, they're talking about these rectangles to show you which part is dy, delta y, and which is the height. So that's what they're asking you to do. But other than that, is really the calculation is calculate integrating with respect to y or integrating with respect to x. It's just a matter of the variable name. It doesn't affect your power rule or any of the rules that we showed you, or even the substitution if you wanted to substitute. It doesn't affect any of that. Okay. I hope this was useful and help you do the homework. We will make another video answering any other homework questions. I did some of the homework problems, but if you have any other homework questions from this set this week, I'll be happy to look at that for you as well. And I hope that you benefit from this lecture. Thank you.